So we saw AST, and we saw that if the three conditions held, then the series was convergent. We also saw that if the third condition didn't hold, then you could always make an nth term argument from there about divergence. The problem is what to do if that third one is fine, but one or two or both one or two fail. And here's an example of that. What's going to allow us to handle this is this new theorem, the absolute convergence test, or ACT. It says instead of looking at the series, if you look at the absolute value of the terms, that series, if it converges, then the original series converges. So let's look at this. So again, let's remind ourselves the UNs are the part without that parity bit there. So what about these? Let's just think about this. Cosine, n squared is no problem. N squared is always positive. Cosine n, though, cosine meanders back and forth. Sometimes it's positive, sometimes it's negative. So greater than 0, not always. So 2 is no good, or 1's no good. 2, well, because of the fact that cosine goes up and down, it's not monotonic, right? Sometimes it's going up, sometimes it's going down, so it fails there. But unfortunately, it's okay on number 3. Remember how we argued something like this back in sequences? Cosine n is between -1 and 1. So you do a sandwich theorem. We're not even going to use this. I'm just trying to show us that we can't use AST. So I'm not going to go through the argument. But you would argue by sandwich theorem that this limit is 0. So you're good there, which the one place you don't want to be. We could have argued an nth term test divergence. So we know nothing at this point. AST is not going to work. Our way out, if 3 fails, of using nth term is not going to work. So what now? Well, let's see if this absolute convergence test can help us out. So no conditions on this. Actually, notice in the statement, it doesn't even say this has to be an alternating series. So imagine that this -1 to the n plus 1 wasn't even there. We could actually do it on that series as well. Cosine n over n squared. Any series you want. So for any series, regardless of what it looks like, if you take the absolute value and that series converges, then the original one does. So let's take a look. So if we take the absolute value of the terms, we're really not taking the absolute value of the series. That would just be of the sum, but just of the individual terms. What does that look like? Well, it's going to do away with the plus, minus, right? Because these are all now non-negative. So really, you don't even have to write that, because that just gets destroyed by the absolute value. It really does nothing to n squared, because n squared is non-negative. So really, you could write that more simply as just absolute value of cosine over n squared. So I want to look at that series. If I can show that that series converges, then that means this one does. That's exactly what our ACT tells us. Well, let's think about our strategy. Things that look like a p-series, which if that cosine n is not there, that is a p-series, right? Things that are close to being a p-series, typically we try and do an LCT or DCT with. And sine and cosine's limits don't exist, but they're bounded very nicely, so DCT. So I want to compare that with 1 over n squared. So let's think about DCT. What do we need? We need these to be non-negative, which they are, right, because of the absolute value. Right? But cosine's never bigger than 1, so I can bound it above by 1 over n squared. And that's a convergent p-series. P is 2, which is bigger than 1. So that means this series, the absolute value, converges by, now think about this, we just did a DCT here, right? Direct comparison test. Then that now tells me by ACT that the original converges. And now you start to see why at the beginning of this whole talk in chapter 10 about series, I said, be very specific. Don't use pronouns like it converges. I want you to be specific about what you're talking about, because look at this. There was a series of, there was this convergence that implied this convergence that implied this convergence. So we're really referring to 3 different series in our argument. And so we want to be very clear when we're concluding what about what series and why. So every time you're saying something about convergence or divergence, state which series you're talking about and give the argument for why you know that. So in the case where AST is not going to work, but 3 is 0 there, you might be able to try ACT. Now the problem is this isn't a cure-all, because that says nothing about what happens if this had been divergent. If you take the absolute value and find out that the absolute value here, this series diverges, no conclusion. So if this had come out divergent, think about if this had just been n instead of n squared. This would have been a divergent situation, and we would have been stuck. So there are some things that won't fall into any of these categories, and because it kind of gets beyond any of the techniques we have, you won't be asked for that, because you wouldn't be able to make the argument. But don't think that if this comes out divergent, you get to conclude that this is divergent. If the absolute value is divergent, you don't know one way or the other about the original series.